Hello everybody, good morning. This presentation will be about taking the concept of columns forward. Now in this presentation what we'll essentially do is that we'll try to distinguish between short and long columns, and we'll try to see what is the basic column design criteria. Now in case of strut or the short column, we have seen that the strength criteria is the determining factor in the effect that when the compressive stress falling on the strut exceeds the compressive strength, we say that a strut fails, right? And in case of long column, we have essentially seen that when the load exceeds the Euler critical load, there is some sort of an instability in the system and the column bends indefinitely. So in case of a long column, it's the buckling or the Euler critical load that is the governing criteria. So in case of long columns, we essentially saw that stability is the main criteria, whereas in case of short column, we saw that strength is the main criteria. Now to distinguish between short and long column, we use a term called the slenderness ratio. Now what is the slenderness ratio all about? For example, let us take that this is a column of length suppose L and radius suppose R1, and this is a column of the same length but radius suppose R2. Slenderness ratio lambda is defined as L by, that is the length by the lateral dimension, that is R. So for this case, obviously lambda, this is lambda 1 suppose, and for this case suppose this is equal to lambda 2. So obvious, it's a very obvious thing that lambda 2 will be greater than lambda 1, as radius of 2 is lesser than radius of 1, and essentially as it is inversely related, so lambda of 2 must be greater than lambda 1. So essentially we see from here that slenderness ratio is a quantity, is the ratio of basically the length by the radius of the cross section, right? And what, or I should say the least lateral dimension, right? And one should note that if there is a thin column, it will have a larger value of slenderness ratio because it's more slender than a thick column. If a column is of larger length, right, then it's also more slender. So if you have a thin column as compared to a thick column, and we have a long column in place of a short column, both of the thin and the long column will have more slenderness ratio. Now the next thing that we want that we'll study is basically what we have learned in the previous lecture, right? Now in the previous lecture what we saw is some kind of a thing like this, wherein the column was rooted to the ground like this, and at the first stage it was subjected to a force suppose P. Now within values of P less than PCR, if a lateral deflection suppose del was given to the column, then essentially if we take the load off, the column retracted back to its original position, right? At P is equal to PCR, there will be some kind of a neutral stable equilibrium in the fact that when I take off the load, the column will not retract to the original position, nor it will bend indefinitely. So this is the point wherein we have the neutral stable equilibrium. And at this point what we did was we utilized this elastic line deflected equation that was essentially what that was equal to y double dash is equal to y double dash, I should say, I'm very sorry, m by ei is equal to y double dash, right? So this was the deflected line equation and we utilized it and found out the value of PCR. Now at values of P greater than PCR, it will be under some sort of, the column will be unstable, right? And it will bend indefinitely once the load is taken off. So this PCR is the critical load. Now what is this value of PCR essentially? As we found out that PCR is nothing but is equal to pi squared EI by L squared, right? And this I is nothing but the second moment of area, so it will be equal to A R squared. Now R square I can bring it on the denominator side, and this I can say is equal to sigma CR to be equal to pi squared E by lambda squared, right? So this is a pretty important relation, and this sigma CR is my Euler critical compressive stress. Now at the point of neutral stable equilibrium, we found out PCR using this deflected curve as some sort of an elastic curve, right? So it's pretty evident from here that Euler critical load is valid for values of sigma CR to be less than the proportional limit, right? That is, if I draw the stress strain curve, essentially with stress on the y-axis and strain on the x-axis, till the proportional limit it will be a straight line. And obviously till this point the column will behave elastically, right? And this is some sort of elastic deflected curve, the equation we got, and then we solved it out. So essentially if sigma CR is at this point, right, so therefore the sigma CR must be less than this sigma at the proportional limit. So sigma CR is less than sigma at the proportional limit. So this is one very important relation, and this is the second relation that we have obtained from this. Now let us move forward with these two relations. Now what we have is, therefore, sigma CR is equal to pi square E by lambda squared, and second thing we have is sigma CR is less than